Consider it is a current carrying loop, and we know that when current flows in a conductor, a magnetic field is produced around it. And today we are going to find out the magnetic field intensity on the axis of a circular loop, current carrying circular loop. Okay, so before going to find out that, we will use Biot-Savart law to find out the total magnetic field intensity at this point due to the current carrying circular loop, right? And I want to tell you that Biot-Savart law, if you remember, Biot-Savart law, dB is equal to mu naught upon 4 pi IDL sine theta upon r square. I think you are familiar with this Biot-Savart law, and already we have discussed, and I want to write here dB is equal to mu naught upon 4 pi IDL sine theta upon r square, right? And we will use Biot-Savart law to find out the total magnetic field intensity due to this current carrying circular loop. And if I take this small element dl is the small current carrying element, and r is the distance, right? R is the distance. And if you see very closely, current carrying loop and r is the distance, and the angle between current carrying element and the distance is 90 degree. So therefore the amount of magnetic field is produced here due to this small element, which is dB, mu naught upon 4 pi, I'm using Biot-Savart law, IDL sine theta upon r square. And sine theta is the angle between distance and the current element, right? And that distance, that angle is 90 degree. And since it is 90 degree, so that this dB, and this dB, the magnitude of dB is mu naught upon 4 pi IDL upon r square. So mu naught upon, so let me write here the small amount of magnetic field intensity, mu naught upon 4 pi IDL upon r square. Point to remember, right? Now, if you think this angle is theta and the total angle is 90 degree, and here in this diagram, if you see, this total angle is 90 degree and this angle is theta, and at the same time the direction of the magnetic field and to the distance, this is also perpendicular, right? So since it is perpendicular, so then this angle theta will be definitely to this angle theta. So therefore we came to know that this angle is theta. And if I want to find out the component of dB, and dB will have two components, dB cos theta and dB sin theta. dB cos theta and dB sin theta. In the same way, if I find out the mirror of this dl, so then we can find out one more angle here, one more current element dl. Same way, because of dl, we will find out one magnetic field here in this direction dB, and it will have also two components, dB cos theta and dB sin theta. And if you remember, this dB cos theta and dB cos theta, they have equal magnitude and opposite direction. They both cancel out each other. Then we find dB sin theta plus dB sin theta, right? Then if I want to find out the total magnetic field due to the entire circular loop, the closed loop, then I have to add all the dB sin theta. And for that we can use integration. So then if I want total magnetic field intensity on its axial line at that point, at the distance x from the center of the loop, so which will be closed integration of dB sin theta, right? So then B, which is equal to closed integral of, instead of dB, can I write this value? Mu naught upon 4 pi IDL upon r square into sin theta. Okay, let me explain you sin theta. So theta is this angle, right? So if you see this right angle triangle, so theta is the angle and this is the opposite side, this is the hypotenuse. Okay, so then sin theta is the ratio of opposite side to hypotenuse, right? So can I write upon small r, where this is the radius and this small r is the distance from dl to the point, right? And x is the distance from center of the loop to the point, right? So then here I can write r upon, right? So in the next step, I want to find out all the constant outside. So mu naught upon 4 pi is the constant. It is outside now. Current is always constant in this loop. And r is the radius constant. And this r, which is the distance, is also constant. So then I can write I into upon r cube square into r cube. Can I write here? Answer is yes. Then the closed integration of dl, right? So in the next step, I can write mu naught upon 4 pi I r cube. And if you see the closed integration, if I add dl, what will be the total length? Total length will be the circumference of the circle. So I can write 2 pi. Any questions so far? No question. 2 pi and 4 pi, which is 2 times, I can cancel. Then I can write here. So let this one be here. So I can write the total magnetic B is equal to mu naught upon 2 IR square upon R cube, right? So in the next step, I can write B is equal to mu naught by 2 IR square. And if you know this, in the question, we will be given the radius of the circular loop and the distance from the distance of the point from the center of the loop, which is x. So then I want to eliminate this. If I want to eliminate this, if you see this is a right angle triangle, if I apply Pythagoras condition, so then Pythagoras condition, then r is equal to r square plus x square. So in the next step, if I want, I can write square root of r square plus x square, right? So then in the next step, I can write mu naught upon 2. Sorry, here I can write. So instead of r cube, I can write r square plus x square and the whole power 3 up 2, right? Now we will find out two special cases when the point is at the center. That means at time the value of x is becoming 0. When x is 0, what will be the magnetic field intensity? Magnetic field intensity at the center. And the second case, when the distance is becoming very, very long compared to r, and what will be the magnetic field intensity? So let us find out two cases. Case 1,